There are two ways that you can represent the dissolution of water by a chemical equation. One is using what's called a molecular equation or a complete formula equation, and the other one is if you're dealing with a strong electrolyte, is you use what's called it's preferable to use what's called an ionic equation. Okay, so how do we write a molecular equation? All you really have to do is write the formula of the solute and indicate its physical state. The solute that you actually added to the water. Was it a solid, liquid, or gas to begin with? Write the formula, and then in parentheses, solid, S, L, or G to indicate whether it's a solid, liquid, or gas. Then you draw an arrow, and then you write the formula of the solid, same formula on the right-hand side, but then label it AQ. And like I said, if the solute happens to be a strong electrolyte, it's completely ionized in water, what you really should do is for the right-hand side, okay, in the aqueous version of your formula, it's preferable that you actually separate the ions. So write the ions separately, okay? So write the ions separately in aqueous solution. Okay. Now, if the solute happens to be insoluble, it's customary to draw a double arrow instead. By double arrow, I mean a right harpoon over a left pointing harpoon. Okay, that's how that figure is, that double arrow is described. Okay, and that's just to emphasize the fact that although you do get some of your solid particles in solution, just very little of it is actually dissolved. Okay, so that's what we mean by insoluble. Insoluble doesn't really mean zero solubility. There's a little bit of your solid that goes into solutions. And to emphasize that, you use a double arrow. Okay, so let's look at a few examples here. Let's look at the chemical equation for this solution of solid barium chloride. So you have BaCl2, solid, right arrow, BaCl2, aqueous. That's your molecular equation. Okay, so this is your molecular equation. It's called a molecular equation is because it's as if that barium chloride is made up of molecules instead of ions, the way you've written it. It's really not. It's really made up of ions. So a really more accurate representation of what happens is to write something like this. BaCl2 solid yields barium ions plus 2 aqueous plus 2 chloride ions aqueous. So this is what you would call your ionic equation. Okay, let's do same thing for glucose. Glucose is C6H12O6. That's a solid. And then if you dissolve it in water, then the product would be C6H12O6 with an AQ label. So this is your molecular equation for the dissolution of glucose. The question is, what is the ionic equation? There is none, because glucose is a molecular compound, and this particular type of molecular compound, most molecular compounds in fact, do not produce ions when you put them in aqueous solution. You remember the 6 exceptions are the 6 strong acids. Now, weak acids, the other acids are weak electrolytes. They produce ions, but not a whole lot of it, so you don't use ionic equations for those either. Okay, so let's take a look at potassium hydroxide, KOH, solid. Molecular equation would be give you KOH aqueous. So this is your molecular equation. Your ionic equation would give you KOH solid yields potassium ions aqueous plus hydroxide ions aqueous. Right? Next, let's look at the other example here. Chalk, calcium carbonate. Well, have you experienced trying to dissolve chalk in water? If If you have, you've probably seen that it would not dissolve in water. Well, when we say it's insoluble, what we actually mean is just a very small amount of it would dissolve. So calcium carbonate, So calcium carbonate is insoluble in water. So calcium carbonate solid yields calcium carbonate aqueous. And what we do to emphasize the fact that it's not soluble is to draw that double arrow, okay? Or to be more consistent with the way it's done in textbooks, you say a right harpoon over a left harpoon. So that's the molecular equation. And your ionic equation would be this, pretty much the same thing, except you know that these ions are not really stuck together in solution. There's dispersed. So you write this as calcium carbonate solid right harpoon over left harpoon, Ca plus 2 aqueous plus carbonate -2 aqueous. Okay, let's look at another example here. Acetic acid, liquid acetic acid. If you have acetic acid, the formula of acetic acid is HC2H3O2. Pure acetic acid, which is a liquid, is also known as glacial acetic acid. So if you mix that with water, you're going to get H plus, you're going to get acetic acid in aqueous solution, HC2H3O2 aqueous. And so this is your molecular equation. You do not have an ionic equation because this is not one of the strong acids. So this is a weak acid. Most of your acetic acid molecules are going to be intact. There's a very small fraction of it that would actually be broken up into H plus and acetate ions. Okay, finally, let's take a look at the last one here. Gaseous ammonia. Ammonia is a gas, NH3 gas. Sorry. NH3 gas. And if you put it in water, that gives you NH3 aqueous. Okay, and that's an example of a base. What actually happens in water, your NH3 will pick up a proton from water, an H plus, and to a certain extent it reacts and ionizes to give you ammonium ions and hydroxide ions. Ammonia is an example of a weak base, okay, because it produces hydroxide ion. So this is a weak base. It's a weak electrolyte. Notice I'm drawing a right harpoon over left harpoon there to indicate that that happens to a very slight extent. So NH3 aqueous, you do not break it up, you do not write it as ammonium plus hydroxide, you simply write it as NH3 aqueous. Okay, there is no ionic equation here. This is your molecular equation for the dissolution.